Starting from the 1950s, alarm bells started ringing as scientists noted a steady decrease in sunlight reaching the Earth's surface. Dubbed global dimming, this trend, which stretched beyond 3 decades till the 1980s, saw a decrease in irradiance of 4.5 per decade. Though solar activity remained usual, the cause was identified to be an increase in atmospheric particles, mainly sulfate aerosols as a fallout of post-World War II industrialization. After the 80s, a reversal in global dimming was noted, parallel to a reduction in particle emissions. This phenomenon, termed global brightening, was, however, partial and inconsistent across the globe. Coupled with disparities in development, countries like Chile, Venezuela, India, and Zimbabwe continued to experience dimming in the 90s. China, albeit falteringly, only started to reverse the trend around 2005. Reductions in evaporation brought on by global dimming disrupted the hydrological cycle, potentially decreasing rainfall and shifting the tropical rain belt. The southward shift could also have reduced evaporation in the tropics, impacting the monsoon season in South Asia, and contributing to a record monsoon failure in 1984 during the Ethiopian famine. This global dimming also obscured the full extent of global warming. Into the future, global brightening is predicted to further progress. As countries respond to the health impacts of air pollution, potentially less global warming will be veiled. Projections from the Intergovernmental Panel on Climate Change have incorporated the impact of particulates, estimating an offset of approximately 5 degrees in global warming. To achieve the climate action targets of 1.5 degrees in 2 decades, projections have accounted for incline in global brightening and correlating decline in global dimming. Human activity had significant impact on climatic changes and the global weather patterns. There was also potential interventions on the global hydrological cycle and regional ecosystems. One of the potential consequences could be the abrupt return of warming, coined as termination shock, if these measures that only offer temporary relief are not sustained for centuries until greenhouse gas concentrations are brought under control. Mikhail Ivanovich Budiko's groundbreaking research in the late 1960s shed light on the ice albedo feedback, an Earth climate system's positive feedback loop. He found that a higher amount of snow and ice leads to more solar radiation reflecting back into space, causing the Earth to cool down and consequently leading to more snow. Other studies propose that external factors like sulfate pollution or a volcano eruption could trigger an ice age. In the 1980s, sunlight was found to be decreasing based on studies in Israel and the Netherlands. Simultaneously, Atsumu Omura of the Swiss Federal Institute of Technology observed that solar radiation hitting Earth's surface dropped considerably in the last 3 decades. Despite the general rise in global temperature since the 1970s, the term global dimming was introduced by Gary Stanhill in the 1990s, when research papers revealed multi-decade declines in Estonia, Germany, and across the former Soviet Union. However, from 2005, scientific papers started reporting a switch from global dimming to global brightening following the implementations of air pollution control measures in developed nations. Emissions, including sulfates, decreased significantly in the U.S. following the passage of the Clean Air Act, which led to cost savings valued at $50 billion annually. By 2010, similar positive changes were observed in Europe after the 1985 Helsinki Protocol to reduce sulfur emissions. The main thematic gist of the story is to highlight human activity's role in causing and reversing changes in global weather patterns and climate. The narrative draws attention to the influence of human activity, particularly in the Northern Hemisphere, on cloud formulation and global brightening. In the last 2 decades, aerosols have increasingly affected clouds, solidifying the evidence for escalating global brightening historically. Global dimming has been associated with higher aerosol concentration in the Earth's atmosphere due to natural dust or volcanic eruptions. However, the impacts of these natural occurrences pales in contrast to the surge in sulfate emissions post-industrial revolution. The alarming growth in human-caused sulfur emissions, surpassing all natural sulfur compound emissions, is documented in the IPCC First Assessment Report. From 3 million tons of sulfur emissions per year in 1860 to about 80 million tons by 1980. The shift exemplifies the dominance of anthropogenic contributions over natural ones in industrialized nations by a factor of 10 or more. Aerosols morph the sunlight's interaction with the Earth's surface, with sulfur dioxide particles reflecting most of it, acting like tiny mirrors. Conversely, the incomplete burning of fossil fuels and wood produces black carbon particles that absorb solar energy, increasing temperature while diminishing sunlight reaching the Earth. Black carbon minimally contributes to ground-level air pollution, but considerably heats the upper atmosphere. Further, atmospheric pollutants also indirectly impact the climate by providing the nuclei on which water droplets in clouds gather. This process leads to more reflective clouds, increasing sunlight reflection back to space while capturing terrestrial radiation within the lower atmosphere. Simulations also hint at reduced rainfall due to these smaller droplets. A study in the 1990s found that macroscopic pollutants caused the sunlight reaching the surface to decrease by 10 under the Asian brown cloud predictions before the research estimated only a 0.51 reduction due to particulates, hence signifying the significant role of particles in cloud formulation. The data constraints and complexities in estimating indirect impacts on clouds precluded the report from determining whether the cumulative effect of human-induced aerosols on global temperature caused cooling or heating. By 1995, the IPCC second assessment report had convincingly established that aerosols generally caused cooling. Nonetheless, aerosols presented the greatest uncertainty in future predictions in that report and others that followed. At the height of global dimming, the warming trend was entirely neutralized, but by 1975, rising greenhouse gas concentrations had surpassed the masking effect and predominated thereafter. Even so, certain areas with high levels of sulfate aerosols from air pollution initially experienced cooling. In contrast to the overall warming trend, an outstanding example is the eastern United States, where temperatures dropped by 0.7 deg. 3 deg. Between 1970 and 1980, and by up to 1 deg 18 degs. 18 degs in Arkansas and Missouri as sulfate pollution was curbed. Central and eastern United States saw a warming trend of 0.3 dc, 0.54 deg. Between 1980 and 2010, even though sulfate particles still constituted about 25% of all tidal. By 2021, the northeastern U.S. coast became one of the most rapidly warming areas in North America, largely due to the slowing of the Atlantic meridional overturning circulation, which raised temperatures in that part of the North Atlantic Ocean. Worldwide, aerosol cooling delayed the onset of extreme heat beyond pre-industrial levels, however. As global dimming subsided, hot extremes accelerated. The reduction in aerosol concentrations since the 1980s, along with the lesser fog, mist, and haze associated with it, was attributed to roughly 10/20 of daytime warming across Europe, and about 50s of the warming in the more polluted Eastern Europe. As aerosol cooling relies on sunlight reflection, improvements in air quality had little to no effect on winter temperatures, but raised temperatures from April to September by approximately 1 deg C, 1.8 deg, 1.8 deg in Central and Eastern Europe. Some acceleration of rising sea levels, as well as Arctic enlargement and the respective Arctic sea ice decline, was also ascribed to the decrease in aerosol masking. Pollution caused by black carbon or soot also contributes to global dimming. However, as it absorbs heat instead of reflecting it, it warms the planet, unlike sulfates that cool it. Climate models began considering the effects of sulfate aerosols alongside the second IPCC assessment report, with all climate models fully incorporating these by the fourth report in 2007. However, only 5 models took less significant particles such as black carbon into account. As of 2021, CUMEP6 models estimated total aerosol cooling between 0.1 deg, 0.1 deg, 0.1 deg, 1.3 deg. The IPCC's sixth assessment report gave a best estimate of 5 dz, 0.90 deg. Cooling due to sulfate aerosols, while noting that black carbon causes about 0.1 deg, 0.1 deg, 0.18 deg. These figures were derived from a blend of model estimates and observational constraints, including data on ocean heat content. The disagreement mainly revolves around the indirect effects of aerosols on clouds. Aerosols are known to increase cloud droplets, enhancing their reflectivity, but determining the impact on liquid water path, a critical cloud property, is challenging due to the extensive calculations of evaporation and condensation within clouds. Most climate models assume aerosols increase liquid water path, yet satellite observations from the 2010s indicated they decrease it instead. A breakthrough happened in 2018 with a model successfully incorporating more complex cloud microphysics. However, a study conducted in 2019 highlighted bias in earlier satellite observations, which overlooked the fact that the thickest, most water-laden clouds naturally rain more and release more particles. Notably, large-scale observations could be confused with changes in atmospheric factors like humidity, demonstrated by findings that air quality improvements post-1980 that would have reduced cloud numbers by about 20s were balanced by the increased humidity caused by the atmospheric response to AMOC slowdown. While initial studies on the 2014-2015 eruption of Bardarbunga suggested sulfates had no effect on liquid water path, subsequent suggestions argue that these findings were skewed by compensation from humidity changes. To dodge such confounding factors, many studies focus on ship tracks. Nevertheless, post-2020 findings posited that visible ship tracks poorly represent other clouds, giving rise to an overestimated aerosol cooling of up to 200. Furthermore, it was later discovered that most of the ship tracks were invisible to satellites, implying that earlier estimates had underestimated aerosol cooling by neglecting these traces. Ultimately, research in 2023 showed that all climate models had underestimated sulfur emissions from volcanoes not associated with major eruptions, leading to overestimates of the cooling caused by human-induced aerosols, especially in the Arctic climate. The projection for a temperature rise of 7 degrees Fahrenheit is now anticipated around 2030, earlier than the mid-2010s estimates of 2040. Experts argue the role of aerosols in regional climatic impacts have been underestimated. For example, a climate scenario with high greenhouse gas emissions but strong reductions in air pollution could result in 2 degrees Celsius more warming by 2050. Regionally, this scenario could add 5 more tropical nights per year in northern China and significantly increase rainfall in northern China and northern India. However, accurate regional projections of aerosols' impacts are difficult due to incomplete historical record. The recent KEMIP-6 climate models struggle to accurately represent aerosol trends in North America and Asia, likely leading to errors in their regional impact forecasts. Aircraft contrails or vapor trails are believed to cause a net increase in radiative forcing. Their warming effect was initially calculated between 3.5 μSU and 17 μN2 and 17 μU2 in 1992. Present estimates sit at 12 EM2 for 2005, though this is subject to uncertainty and a low level of scientific understanding. Contrail cirrus, air traffic's largest radiative forcing component, could triple from a 2006 baseline to 180 MMU by 2050 without intervention. Contrail effects vary based on their formation timing, where daytime contrails have a cooling effect while nighttime flights contribute to warming, leading to a substantial diurnal temperature variation. When commercial aircraft flights were suspended after the September 11 attacks, the diurnal temperature variation widened by 11 degrees Celsius. In a 2011 study analyzing UK meteorological data from World War II, a single event showed that following the movement of USAF strategic bombers, temperatures rose by 0.8 deg 1.4 depth, above the average close to the air bases. The sweeping changes brought by the global response to the COVID-19 pandemic in 2020, which saw a 70% reduction in worldwide air traffic, opened a unique window of opportunity to investigate contrail's effect on regional and global temperatures. Results were inconclusive, with no significant alterations in diurnal surface air temperature range, either minimal or no net significant global warming impact. Conversely, the reduction in sulfate emissions caused by diminished road usage and industrial activity during lockdowns had a discernible warming effect, escalating global temperatures initially by 0.1, 0.2 dec, 0.36 dec, potentially rising to 3 dec C, 0.54 dec, predicted to disappear. Air pollution possesses the power to influence the water cycle on a regional and global scale, akin to certain natural phenomena. Examples include Sahara dust's impact on hurricane formation, which cools ocean surface temperatures, thereby mitigating hurricane development and decreasing evaporation from the ocean. This, in turn, slows down the planet's hydrological cycle. Research conducted in 2011 revealed that human-produced aerosols were the primary force behind changes in Atlantic Ocean sector rainfall during the 20th century, contributing to shifts in the tropical rain belt. Considering the link between aerosols from the Northern Hemisphere and the monsoon failures in sub-Saharan Africa during the 1970s and 1980s, it is likely that sulfate pollution exacerbated the severity of the drought in the Sahel region. Furthermore, The influence of aerosols on climate has also been tied to the weakening of the South Asian monsoon. Despite the challenge of proving whether the drought would have happened absent aerosol pollution, the research paints a stark picture of human-induced aerosols' impact on climatic patterns and weather events. The study suggests that aerosol pollution over South and East Asia not only reduced rainfall in these areas, but also contributed to increased summer rainfall in Central Asia. The same link between aerosol concentrations and alterations in rainfall patterns was also made in the IPCC Sixth Assessment Report for the Mediterranean region. The discourse of increasing the planet's albedo by 1 to counteract the radiative force from greenhouse gas emissions and by 2s to offset the warming effects of doubled atmospheric carbon dioxide concentration is under consideration in theory. This principle underpins solar geoengineering. For a long time, the highly reflective nature of sulfate aerosols has led scientists to consider using them for this purpose. Back in 1974, Mikhail Budikov proposed that to combat global warming, sulfur could be burned in the stratosphere to create a cooling haze. Attempting this approach today would negate decades' worth of improved air quality and bring back issues such as acid rain. As such, utilizing tropospheric global dimming to combat warming is considered a Faustian bargain and is not taken seriously in contemporary research. Building on Paul Crutzen's influential 2006 paper, current research favors stratospheric aerosol injection or SET. This involves transporting sulfates into the stratosphere, a higher layer of the atmosphere, where these particles could remain for years rather than weeks, thus requiring less sulfur emissions. It is estimated that the sulfur amount needed to counteract a warming of around 4 days relative to current temperatures and 5 days relative to pre-industrial times under the RCP 85 high emission scenario is less than current air pollution emissions. It is further projected that future reductions in sulfur pollution due to anticipated air quality improvements will offset the sulfur required for geoengineering. However, this approach comes with increased cost. Contrary to popular belief, stratospheric aerosol injections require a significant financial commitment, with estimates to cool the atmosphere by on-deck costing around $18 billion annually. Consequently, only major economies or economic blocs could afford this intervention. Ironically, these methods would still be significantly cheaper than greenhouse gas mitigation or the cost of dealing with the consequences of climate change if left unchecked. However, the main disadvantage with C is the short-lived cooling effect, which would cease 3 years after the last aerosol injection. Conversely, the warming effects from CO2 emissions can persist for centuries unless counteracted earlier. The prevailing view is that, compared to current conditions, crop cultivation and carbon sequestration might remain largely unaltered or even experience a marginal increase. This is because the diminished photosynthesis due to lesser sunlight may be counterbalanced by the effects of CO2 fertilization and thermal stress reduction. However, the impact on particular ecosystems is less certain. Additionally, it's probable that stratospheric aerosol injection could increase the death toll from skin cancer due to the diminishing ozone layer. On the other hand, it could reduce deaths from ground-level ozone, making the overall impact ambiguous. It is also anticipated that changes in rainfall could alter mosquito habitats, significantly impacting the distribution and spread of diseases transmitted by these vectors. The effects of this, however, remain uncertain.